Thanks, Greg. Although you ruined my joke, because I was going to say, hi, I'm TBD, because Brad asked me yesterday if I could chair the session. Okay, so yeah, we're going to start off a session for the speakers, 10 minutes. I'll give you a warning, and then another 2 minutes to wrap up, and then we'll do questions. The session is called Crust and Dust. We have a bimodal distribution here between really interesting far side feldspathic highland terrain targets and also both science and hazards of dust. So we'll get started. And the first speaker is Benjamin Greenhagen. Uh-oh. Yay, okay. All right, so I'm going to start off by talking about Moscoviense Basin and why it's a really interesting place where you can get a whole bunch of different crustal lithologies, basically the whole column from the surface to the lower crust in one location. Nope, that was the wrong button. Oh, that was the right button. Okay, so start off, why Moscoviense? Why is it so awesome? Well, it's a pretty unique, large multi-ring basin. I'll talk about those unique properties in a minute. It has the excellent crustal compositional diversity I mentioned before, and this is what was really driving my interest in Moscoviense leading into this meeting. Far side, Mare volcanism, the biggest area of Mare volcanism in the feldspathic highlands terrain. It even has swirls. And here's a couple of kind of historical context images. This is the first image to include the lunar far side from Luna 3. The second image it ultimately returned. And there's this big, oh no, it doesn't work, big blotch here on the far side, which was Sea of Muscovy was named, and now Mare Moscoviense. Later did they discover that there was a basin around it, and so now we call it Moscoviense Basin. All right, multi-ring impact basin. It's Nectarian in age. Ooh, I'm used to pointing more than this. About 3.9 billion years old. In the stratigraphy of basins, it's the 7th youngest basin, and very isolated from most of the other basins of similar age. The rings have been kind of an enigma over the years. There's been a number of folks that have mapped out the rings, and most people get different values. The floor here, especially with the Mare fill, is this very elongated shape. Some people have referred to it as a kind of rectangle shape that's slanted. Has non-concentric rings. Oh. It's actually a little bit easier to see here. This is a WAC shaded relief map. It's a little bit easier to see the features of the basin here. This is the inner ring, the peak ring, I should say, inner ring. The middle ring, so the peak ring it represents the lowest material that was excavated. The middle ring represents the edge of the transient crater during formation, and then the outer ring, which represents the region that has slumped following basin formation. Also has this is one of the unique features here is that it has these rings, but they are not concentric. They do not have the same center point that the other basins have. Has some evidence for discontinuous ejecta, has the thinnest crust on the moon, although some people would say Crisium has the same, but this is a very different geologic setting. It's in the thick feldspathic highlands terrain, so all of this material around it is having crustal thicknesses of 60 kilometers or thicker, and the crustal thickness in the center of the basin here is approximately 0. It has a gravity anomaly, and of course the Mare deposits, which I mentioned a second ago. And here's the map from Bazoric that incorporated both the Grail data and the Lola data to map the crustal thickness. Moscoviense is there, and Crisium is there, the two thinnest places. So Thyssen et al. 2011 wrote a very nice paper, talked about the geology of Moscoviense, and in the paper they talked some about the origin. And these were the 4 hypotheses that they put out there that had been somewhat discussed in literature previously for the formation. The simplest is a single oblique impact, which can explain basically all of the surface features that you would see. It explained the partial peak ring, the elongated floor, the regional slopes, and the discontinuous ejecta. It can't explain any of the subsurface features, which were not as well understood until we got the more recent data sets, starting with Kaguya. And that's the thin crust, the gravity anomaly, and the Mare deposits. So A couple of additional hypotheses came up to explain this. One is that it impacted into existing basin. This basin has been coined by Chuck Wood as the Appleton Zoo Basin. And by having a coincident location for Moscoviense into this other basin, you can get these similar features. Thiessen et al. Also proposed a double impact. This would be something perhaps akin to what we would see if a meteorite was, or a large object, asteroid was coming in and broke up close to the moon and had an almost simultaneous impact between two chunks that were slightly offset in their impact direction. And that could also explain everything. And then the third is that it was simply an oblique impact, but it was into an area that already had a crustal anomaly. In this case, the anomaly would be kind of plutonic intrusions into the lower part of the crust. All right, so one of the things that's really interesting with Moscoviense is the diversity of composition in the basin ring. This is a mosaic of M-cube data that Carrie Donaldson-Hanna put together for me. A lot of the mafic crustal diversity is coming right in the peak ring, this innermost ring of the basin. The middle ring, which is the shallowest material excavated, does have some exposures of the pure stanorthosite or pure crystalline plagioclase. No highly silicic evolved lithologies. If we had that, we really would be a slam dunk on lunar crustal diversity, but we don't have that here, not unexpected. Although we do see mafics in the area that are extending beyond just the peak ring. There are some in the spaces that are between the peak ring and the middle ring. So this is a region that was highlighted in Carly Peters' paper in 2011 with the ooze, the orthopyroxene, olivine, and magnesium aluminum spinel, and highlighting these really interesting mafic compositions. These are not little tiny compositions. These are not things that are brought up by small impact craters. These are exposures of large kilometer-scale deposits, which I really like for the resolution of the data set I usually use, which is Diviner. They're mature. They have a well-developed regolith on top of them. They're not disturbed. And their position in the peak ring and then also amongst these very anorthositic materials of the peak ring suggests that they are from the lower crust, perhaps near the crust mantle boundary, and they formed as differentiated magmatic intrusions. And so these pictures here are showing some of the different parameters. The mafic exposures happen independently. For instance, here's an olivine by itself, and down here even orthopyroxene and spinel by itself. And they can also happen in close proximity to each other. Here's an olivine and an orthopyroxene and spinel and orthopyroxene. Worked with Paul Lucy a few years ago to start an effort to revise his mineral mapping algorithms that he had produced back in 2004. And but now using the multiband imager data. Lemelin et al. Has talked about this number of conferences, and the data is available on the USGS, but the publication isn't quite out yet, that basically uses Hapke modeling of near-infrared spectral parameters to reproduce the observed spectra, and then using iron as the constraining parameter. And unfortunately, I did not set a timer for myself, so we'll just see how this goes. The thing that we're bringing into this more recently is the Diviner data, and what we're doing here is using the very high sensitivity that the thermal infrared has to the plagioclase mafic ratio in order to constrain the plagioclase abundance. And this was actually one of the things that Carly pointed out in her paper, is that the abundance of the plagioclase is not well constrained, and so that limits what we can say about the purity of whether it's a peroxenite or whatnot. And with including the infrared data, we're really starting to get at an area where we can say these are pretty mafic. This particular one here has a plagioclase abundance of less than 30, which is about as low as we see anywhere on the moon. This is just another example where with the near-infrared only mapping, you see a lot of olivine is modeled to be in the crust. When you add the thermal infrared constraint, you're able to locate it to specific geologic features. In this case, these are craters that are poking into this interstitial region between the inner ring and the outer ring to pull up olivine exposures. All right, so the Mare basalt compositions, George Kramer had a very nice paper using Clementine data back in 2008 and looked at the Mare compositions in this area you have both high and low iron. This is a Clementine iron map. You also have high and low titanium. This is the titanium. And then you potentially also have alumina. This is the map that George produced and mapped out the different units. This is the oldest unit, would be the red unit here. The middle-aged units would be this orange unit and the green unit, and the youngest unit would be the purple unit, which corresponds with the highest titanium abundances. Now, for the constellation site, it was chosen to go to the site right here at the edge of the basin floor material and the high titanium basalts, potentially for IRCU possibilities. And this is a quantification of the strategic relationships that were identified earlier, showing that the oldest MAR units are approximately 3.9 billion years. The middle units are 3.5 to 3.7, and the youngest units are pretty young at 2.6. And this is work that Haruyama and Moroda have done. And then there's also a nice correlation here between the estimated volumes of basalts produced and the age, where you started off with the highest volumes, and then it decreased in volume as time went on. And finally, I know they're going to talk a lot about swirls tomorrow, so I'm not going to go into it too much, but there is a weak magnetic anomaly in the work that Dave Blewett did a few years ago, 2011. This was actually the weakest anomaly that he included in his study, but thank you, Dave, for including it. These are the swirls. They're mostly located in that oldest unit, in the middle unit, which is located very conveniently right next to the OOSs. But there are some also in the younger high titanium basalts as well. So I think I'm pretty much out of time, but I just wanted to get out there that Moscoviense has a lot of different things going on. You can imagine lots of single-day missions, which would choose any individual type of study that you want to do. You also could do lots of interesting sample return missions, including the Basin impact melt, these lower crust mafics, the spinels, pure plagioclase, far side Mari basalts for the first time. You also have a far side swirl if you want to monitor. And then you can imagine all kinds of roving experiments. Now, you have to be a little careful because Moscoviense is big. The region of interest that we've been talking about here is about the same size as Iowa. So if you're going to be doing a roving experience, it's going to have to be MSL++++, or some capability that can go more like 100 kilometers or more instead of just the 20-ish kilometers we've been talking about otherwise. But with that, I think we'll finish up. Thank you. All right. And if there's any questions, I think we have about 1 minute. Otherwise,
Ben?
Oh, yep.
Okay. So could you just clarify, I missed the assemblage. So if I understood, you saw the magnesium, the spinel with, or the pyroxene with plagioclase, or you inferred plagioclase is with the pyroxene?
Yeah, so the peak ring composition is mostly a plagioclase-rich matrix. So there's plagioclase everywhere in there. For the composition of the spinel orthopyroxene, it's really just varying amounts of plagioclase. We have to be a little careful, though, when we say that's not a proxenite by including the diviner data, because it could be, and it could just be that there's 15% material that's infall on it that conceals it to us as well. Okay. All right, so next up we have Jack Wilson, and he's going to be talking about kilometer-scale regions of primordial flotation crust that may be accessible in Hertzsprung Basin.
Okay, thank you. Yeah, so I'm going to try and convince you that if you want to find somewhere where you can fairly easily access a sample of plagioclase-rich primary crust, Hertzsprung is a pretty good bet. So I'll start with a bit too much background. To go right back to the start, the anorthositic nature of the feldspathic highlands terrain was first postulated on the basis of Faroe anorthosites found in Apollo samples. So the geochemistry of these minerals, including a sort of high anorthite-rich plagioclase content, low iron abundances, and rare earth element depletion, led to the hypothesis that the lunar highlands formed from the crystallization and flotation from a global magma ocean. So an important question to answer then is, what's the content, what's the composition of the primary crust, because that tells you how this crystallization occurred. So recently, there have been several studies that have identified sort of 100-meter scale outcrops of nearly pure anorthosite across the moon globally. This here is from Otake et al. 2009 and is based on Selene spectral profiler data. Although these outcrops occur globally, they are concentrated within the Feldspathic Highlands terrain, and they occur exclusively only where there are craters or basins larger than 100 kilometers in diameter. And the only regions where there are multiple exposures at the surface are found to be where there are relatively recent impact craters or steep sloped peak rings or central peaks in craters. So these two observations have led to the idea that there's a more or less global layer of plagioclase-rich material buried between 3 and 30 kilometers beneath the surface. And that when it's brought to the surface, space weathering fairly quickly on reasonably short timescales removes the spectral signature of this plagioclase. Okay, and one of the locations where these pure anorthosite outcrops occur is Hertzsprung Basin. Hertzsprung is a Nectarian-age basin that's around 570 kilometers in diameter, although that's quite difficult to determine. It's intermediate in size between Schrödinger, which is off to the southeast, Oriental, which is a true multi-ring basin off to the southeast, and sort of peaked basin like Schrödinger, and as such it excavates material to intermediate depths as well. So it samples roughly the top 40 kilometers, which is about half the crust, with most of the material being from the top 25 kilometers. So if we take a look at the Clementine iron oxide abundance, we can see that the ejecta from Hertzsprung is fairly feldspathic. In fact, it's very feldspathic, and the peak ring itself has almost no iron oxide signature. In the southeast of the basin here, you can see there's a slight excess of iron oxide. That's most likely Orientale ejecta and isn't related to Hertzsprung. Additionally, there's the ejecta is high albedo, and there's a particularly high albedo signature between the inner and outer ring on the west side of the basin. Plot here in low albedo data. So both of these things again suggest that you have a large degree of plagioclase-rich material in Hertzsprung. So the pure or nearly pure anorthosite outcrops are plot here as red points in the basin. These white points are what Yamamoto et al. Call the featureless spectra based on Clementine data, Selene data. And they've hypothesized that these are essentially nearly pure anorthosite outcrops that have been weathered over time and so lost their spectral features. All right, but I could have said all of that about pretty much any basin on the lunar far side, I think. Certainly Korolev, Orientale, more or less Moscoviense. So what is it that makes Hertzsprung unique? Well, one of the things is in the thermal neutron data. So thermal neutrons on the moon, essentially they're a measure of what the concentration of the neutron-absorbing elements is in the regolith. And in lunar soils, neutron-absorbing elements means iron, titanium, and rare earths. So in this thermal neutron data, Hertzsprung stands out essentially more than anything else, which tells you that you have no iron, essentially, and very little in the way of rare earth elements. In fact, it turns out that you can estimate the plagioclase content of the top sort of few tens of centimeters of the basin using thermal neutron data. This is outlined in full in Peplowski et al. 2016, but the basic idea behind it is that thermal neutrons are roughly inversely proportional to macroscopic neutron absorption cross-section. And you know that the dominant contribution to the lunar crust is made up of just 4 minerals, plagioclase, pyroxene, olivine, and ilmenite. So using these 2 facts and essentially the elemental abundance data from thermal neutrons, you can estimate the mineralogical composition. And if you do that, it turns out that at Hertzsprung you have around 85% calcium-rich plagioclase over a fairly wide, sort of few hundred kilometer region, which is great. But as has been pointed out in other talks, the lunar prospects and neutron data have this feature that essentially your footprint is sort of 45 kilometers across, so what you're viewing is a slightly smoothed, blurred version of the truth. And ideally you want to recover what's really going on the surface. So one way of doing that is with image reconstruction. Essentially you say we have our data and we want to recover our image. Because of the presence of noise, that can't be done analytically, but you come up with some statistical techniques. In practice, what this looks like is we have a true image, which in our case is the distribution of plagioclase. Observation with an instrument causes that to be blurred with this point spread function that smooths everything out, and you also add some noise, which makes things more difficult to make out. After going through reconstruction, you ideally recover something that looks quite a lot like the original signal. It's not perfect, of course. The presence of noise means that it's impossible to recover exactly what you started with. But when you send the lunar prospect to thermal neutron data through this process, what you see is that what was a very broad thermal neutron enhancement is now confined more or less between the inner and outer peak rings of the basin. And this corresponds very well with the high albedo region and also the area where you get these featureless spectra in Cellini data. Additionally, because you've sort of sharpened things up and squeezed the signal in a bit, the dynamic range increases by 66%. So what that does is it takes our estimate of the anorthosite content to greater than 95% with a roughly 5% error. And this is exposed over a 100-kilometer diameter region. So given that this content is so high, it's impossible that it could be buried under more than a centimetre so of regolith with more iron or more rare earth, say. Because if it were, that would swamp the neutron signal. So what we have here is an easily accessible region of essentially pure anorthosite on the surface. And that means that you could essentially send a lander here and not have to bother with a rover, not have to bother trying to scale these crater rims or peak ring or crater peaks in order to search out these clean deposits. It looks like they do exist on the surface, but weathering makes them invisible to spectral sampling. So this is very interesting because it's a sort of outlier in terms of being plagioclase rich on the surface. But of course, one of the problems is that because it's such a strong signal in the thermal neutron data, that means you have essentially no rare earth elements. And the rare earth elements are one of the things that you want to characterize when you're looking at these samples. So that means that unlike on other missions where you'd be looking to recover, say, a kilo of something that was basalt rich or glassy in order to determine the composition perfectly, for Hertzsprung, you're going to need a somewhat larger sample size. But if you do get hold of it, then you can immediately answer 2 of the science goals. That is, determine the composition of the lower crust and bulk of the moon, and determine the extent and composition of the primary feldspathic crust. the composition part there is obvious, but the extent comes from the fact that what you're doing here is you're providing the remote sensing data a ground truth. That's a big problem that we have at the moment, that essentially for the far side, when you're performing this conversion between plagioclase and thermal neutrons, we're outside of the area that was sampled by the Apollo missions. So if we could get that, we could drive the errors down from that 5% and get a good estimate of globally how the plagioclase is distributed. Additionally, we can answer 1C, which is is to try and get a sort of precise absolute determination of the ages of chronology of major basins. So we can sample Oriental Hertzsprung ejecta here, which is in peach and orange, but additionally in this high plagioclase region, we have Oriental ejecta, which is in blue. Recovering that sample lets us characterize both of these. As Ben is stood up, I will leave my conclusions there and say thank you.
Any questions for Jack?
So I think this is a really interesting problem. I think most people in the room are aware of. And you did mention that you'd need a large sample if you returned a sample, but you didn't mention that you would use it for chronology. And it's the underpinning of the lunar magma ocean model and the chronology. So that's something you should definitely include.
I agree, yes.
Have you had a chance to look at the work that Donaldson-Hanna did looking at the crystalline plagioclase? Because she finds a large amount of the strongly crystalline pan in that area.
That's very interesting. I have not, and I will certainly do that. Mm-hmm. Yes, thank you. Just out of curiosity, what's a large amount?
As I recall, and I'd have to go back and read the paper, she found it mostly exposed by small, fresh craters. So it was because this is an old highland terrain, that the small, fresh craters expose the pan very nicely.
Right.
And there's like 10 or 15 of them around, so there's a real cluster of the pan in that area. So it's a nice coordinated study that works out quite well.
Yeah, that sounds right. Thank you. Okay.
Okay, our next speaker is Chu Wang, In-situ measurements of electrostatically lofted dust on the lunar surface.
So how many minutes do I have?
10 minutes, and then I'll wave at you, and then 2 more minutes.
Okay, so I try to speak as fast as possible. I prepared for 15 minutes. Anyway, so this talk will be a little bit different. We'll have electrons and ions. And so the first evidence of electrostatic dust transport was this so-called lunar horizon glow. So this image is, those images taken by Surveyor 7, and you see this bright glow right above lunar horizon. And so there's no air, no clouds on the moon. So what is this? It must be caused by lifted dust particles. But then the question is how these dust particles get lofted. One would think it's due to meteorite bombardment, but the rate was too slow to give you this bright glow. So then people proposed the electrostatic lofting mechanism. This is because we know the lunar surface is charged due to direct exposure to solar wind plasma and solar radiation. So dust particles are charged and may be moved by electrostatic force. So there are another 2 observations from Apollo missions. On the left is the sketch drawn by Apollo 17 astronauts. Maybe Jack Smith can tell more about this. So you see this pattern like streamers reaching high altitudes. And also this is the lunar ejecta meteorites experiment. The LEAM was designed to measure hypervelocity impacts, but instead it measured many low velocity impacts, and mostly occurred at sunrise and sunset. So beyond the moon, several observations from other LS bodies and also tied to this electrostatic dust transport. So this is the radial spokes in certain rings. And this is dust ponds, very fine dust deposits at the bottom of the craters on asteroid arrows. And recently, Rosetta collected dust particles from the comet 67P when the comet was far from the sun. So this the fundamental question is how dust particles get enough charge to be lofted or transported. So it wasn't clear for decades until recently. So we have these laboratory experiments that greatly advanced our understanding of this process. So this is the movie I will bring down. So it's hard to do this. Oh boy, okay, if you can look carefully, you see the particles hopping off the surface, and just by exposure to UV lamp or plasmas. And we did a bunch of experiments about lofting or non-lofting conditions. So we came out with this new charging model. It's called patch charge model. And one uniqueness of a regular surface that is different from solid surface is those microcavities. So I will make sure, so the cavities can absorb photoelectrons or secondary electrons generated from photons or primary electrons. And those emitted electrons will be absorbed inside the cavities, so they don't get out. They will charge those red patches negatively, and those negative charges will repel each other to eject dust particle of the surface. And so we measure the heights and the speeds. So the maximum speed is about 1 meter per second. The height is about 2 centimeters. And this is limited by camera resolution, so those can be even higher. So anyway, 2 centimeters on Earth is about 12 centimeters on Moon. That's about the right height of the lunar horizon glow. And so then you would think, so we can move dust, we can loft them, we can transport them. What happens to the surface properties? There are two movies. On the left, you will see so we can turn the rough surface into a smooth surface. I put the image of dust pond on the top to refer to you, so what this means. And on the right, we put 2 permanent magnets below the surface. The purpose was to investigate dust dynamics in the lunar magnetic anomaly regions, because lunar swirls associated with those crustal magnetic fields. So if I turn on the movie, all right, so you see what happens. It gives you very complex patterns. It gives you this heart shape and also the sand dunes, wavy things. We don't understand what's going on there yet, but this is what we're working on.
Excuse me, how large the scale?
The crater is only 2 centimeters in that, yeah. And this is only just on the UV light, very, very simple setup. And so I have shown laboratory experiments to show we can indeed lift dust, move dust by just electrostatic force. So it has very important implications. They can change the surface morphology, porosity, and thermal inertia. They can redistribute surface materials. It can change the space weathering effects. So we think we have lab evidence, we have related in-situ observations, and now we have a theory to back it up. We think it's a good time to go to the moon or airless bodies to find the ground truth. So this is a CubeSat electrostatic dust analyzer we're developing at the University of Colorado. So the idea is to put it on the moon or on airless bodies. It's a 6U CubeSat with a 2U dust sensor. So this is how dust sensor works. So the goal is to measure charge, velocity, and mass. So this really identifies electrostatic lofted dust. And very important, we like to know the flux. So the flux tells how fast this process goes on the surface. So velocity range will be low. It's 0.100 meters per second. And the sensor is made of like 2 components. We have dust trajectory sensors on both ends of the instrument. And we have deflection field electrodes in between. So when a dust particle comes through the trajectory sensor, so you induce charge on the wires, those wire electrodes, and will be measured. So, and also we have 2 wire electrode planes, so then we can get the velocity. And the particles will get deflected in the deflection region and exist through another trajectory sensor. So we can recover the full trajectory, and then we can get a charge to mass ratio. The charge is measured from here, and then we can determine the mass. So it will be integrated in the 6U CubeSat. So CubeSat can be deployed from a lander or rover or even by astronauts. So by astronauts it will be easier for the design because they can be positioned by astronauts for the best position to take the measurements. If by rover or lander, it has to be self-positioned. So we designed autonomous features. So we have some sensors around the CubeSat, so we can determine where the sun is. And then we have miniature linear motion actuators, so we can tilt up the sensor for large field of view. And the raised up side should be away from the sun. And we have a door in the back to block the solar wind plasma and solar UV from entering the instrument. And all right, so for the landing site, so based on our experiments, so we need either photoelectrons or singular electrons. And photo emission is always a dominating charging source in space. So we have relatively low requirements. We just need a site in the sunlight. And that's it. So which means lower latitudes will be better, but it's not limited to that. And multiple sites will be good. You know, the flat regions, that's the baseline. We like to put this in the craters because you have these terrain regions can create late shadowed boundaries that may enhance electrostatic dust transport. And of course, lunar magnetic anomaly regions, we like to know how dust behave in there and how that contribute to the formation of swirls. And it can be deployed from land or rover or even by astronauts. It's not sample return, it's in-situ measurement. We don't need the mobility. And I think that's it. Did I make it? Great.
Maybe you said this and I didn't catch it. Can this last through the night and operate over multiple lunar days?
I think during the night you can turn it off because we think the charge is usually from the photoelectrons.
Well, don't you want to see what happens at dawn and dusk?
Yeah, that's during the crossing, yes.
Yeah.
Yes, that's definitely the interesting, yeah, the period, yes.
So do you physically have to, I'm thinking how autonomous is. Is this something you can just go put on the surface and let it sit there, or do you have to?
Yes, yes. You can just eject from lander.
Yeah.
And it will reposition, like, you know, to get a large field of view.
But you don't have to go up and just turn it on and off. It can do it itself.
Yeah.
That's cool.
It's kind of similar to Carly's question. So do you expect to see the particles like after they were lifted, like go to a certain direction, or just like lifted and stay there?
Well, you will collect dust particles when they go through the instrument, right?
No, I mean like when the particle on the surface was lifted by the electrostatic field. So do you expect the particles goes to somewhere else or just lifted there?
You mean floating?
Yeah.
Oh, you don't know if it's floating or not, because it's floating, you can't measure it. You have to measure something goes into, come back, it's falling back.
Okay, so falling back on the same location or different location? You don't know?
That doesn't matter, it just, you know, you can collect it by your instrument.
Okay.
So you showed dust hopping with UV light, but as your first bullet there points out, it's actually sunlight, a full spectrum that's falling on the lunar surface. Do you think the other wavelengths are going to quench your effect?
So you need the short wavelengths, yes. So the energy is from you have the energy should be higher than the surface work function. in order to emit photoelectrons. So the work function is usually about 5 eV, so you need a wavelength shorter than like 200 nanometers, and that will give you the photoelectrons. So shorter is better, because higher energy means higher charge.
Nobody has ever explained, and I've been saying this now for several decades, if dust is being levitated and moved, why isn't it on the rock surfaces, the flat rock surfaces?
Yes, there are a lot of questions, to puzzle us. And actually, what we're working on is in the lab, to simulate the photon flux at 1 AU and see what happens. What's the lofting rate? And
But, over geologic time,
over geological time, yes.
You would expect that the dust, the only answers I can see is that a levitated particle goes up and comes directly back down, or it never comes down. But the rock surfaces are fresh. They don't have dust on them.
Yes, that's a great question.
They have ejecta on them some
Yeah,
places, but
and,
not this very fine dust that you're talking about.
Yeah. So it depends on many things. Many things determine how dust move. Not everywhere you can move dust.
All right, final question, Dave.
How far developed is your instrument? Do you have a Picasso or Matisse or funding like that, TRL level?
So I think we're working on, we have TRL3. We're building the prototype and hopefully to get to TRL4 soon.
Great, thank you very much.
Thanks.
All right, and the final speaker is Brian O'Brien, which is going to be a remote talk towards risk management of movements of fine dust on surface of the moon, reality checks from Apollo 11 to Chang'e 3-4. Brian, can you hear us?
I can hear you, thanks. My own business?
Yep.
Okay, well, the first thing is I'm delighted, of course, to join you in this session and thank Clive, Greg, and Ricky for all their help. I regret that it's only remote and that I've not had yet the opportunity for any personal discussions one-on-one. However, I will be at the Denver conference at the end of February, and perhaps we can pick up discussions if you wish at that time. Next slide. Because this is remote, I'm relying on you all to read the text and in the others, and I'll comment only on particular issues. Basically, the point I'm trying to make with this slide is that the step-by-step accumulation of knowledge into the 2007 report and then into a review of that report and so on does not apply to dust. Have the next slide. Instead, I'm suggesting that you use the Kuhn cycle, shown as a black and white clockwise cycle here. And what you see at the moment, you're seeing the pre-science phase of that. But just very quickly go around that clock cycle there. You'll see that until about 6 o'clock, a model was muddling along, and that's about the case with dust. Then at 6 o'clock, you had a crisis, and we'll go from there to the next slide. It's now populated as of now, and we go through that. It was populated between 2014 and 2016 with the U2 crisis at 6 o'clock. And then at 8 p.m. is my sunrise revolutionary discovery. and that's leading on to a paradigm change, the increased priority of dust at 10 p.m. Now on that slide, you'll see at 6 o'clock the U2 immobilization crisis. At 8 o'clock, the sunrise-driven dust storms, and at about 10 o'clock, the paradigm change with regard to the priorities of Chang'e 4. Next slide. So on the left-hand side is the Chinese situation. At the European Lunar Science Conference in 2016, Zhu et al. Said that Chang'e 4 would be revising its priorities to make dust the #1 priority. But as I've noted in the second dot point on the left-hand side, as of December, this is not yet confirmed, but there's very opaque communications. Now go to the right column. USA Apollo mine sets were established in 1964 with the Ranger 7 first photos showing a rock calmly sitting on the floor on the surface of the moon. And I strongly recommend you Google Noel Innes, the distinguished NASA headquarters and agency person, to get you a lively account of the dismissal of dust at that time. Second dot point on the right-hand side is that even at Apollo 17, as Jack would verify, there were severe dust problems even after the previous missions and after all the capability of the technology at the time. Apollo 17 ended with the dust problems essentially unfinished business. Now I'll go to the next slide. Next slide, please. My involvement with lunar dust was purely serendipity, because in 1966 there was an assembly of the 7 principal investigators for all the LSEPs. We were briefed by the 2 aerospace companies that were going to bid for building the LSEPs, and by NASA, to the effect that Conway Snyder, John Freeman and I were told our radiation experiments must put a dust cover over the apertures through which the radiation was to enter. The reason given was to guard against possible dust mobilized by rocket exhausts as the astronauts left. I asked at the time on each day, quite reasonably I thought, who was going to measure the hypothetical dust against which the retractable dust covers would be guarding. On each day I was told, quite unreasonably I thought, by aerospace companies and NASA, that no dust detector was necessary. Going home to Houston from LA after a double scotch before dinner, I invented the dust detector experiment, of which 4 are now on the moon. That slide in front of you shows the removable dust cover, which also reminds us that the photographs of the Hasselblad photographs taken before the ascent of the lunar modules do not necessarily accurately reflect their present condition. Certainly, steeply there in the middle, the dust cover was removed, and we had fun for quite some time. Next slide. Left-hand side is the original invention of the dust detector. And the modified Apollo 12 one on the right-hand side. I noticed for those concerned about contamination by astronauts, for example, you'll see the little splashes of moon dust on the PCU on the right, very close to the dust detector, in fact. That turned out to be quite useful because some collateral dust, as I call it, was splashed onto the dust detector itself. And then on Apollo 12, when the lunar module took off, the effect of the rocket exhausts was to clean that off again, which was a delightful experiment and very informative one. Next one. Next slide, please. Thank you. Okay, so how does this little simple dust detector work? I'll let you read that through for yourself, please.
Two-minute warning, Brian.
Yes. The third dot point from the bottom, that the dust on the cell causes a percentage change in voltage. I make the point that that's fungible. That's a very important point for sharing the information. I only had one calibration against which to convert the percentage change to an amount in simulated dust in milligram per square centimetre. But if you don't like the choice I made, get your own solar cell and put your preferred dust on that until you match the percentage change that historically has been reported by the DDEs. And Bob's your uncle. Next slide, please. U2 is shown on the left. I'm sure most of you are aware of that. The immobilization of it in January 2014, after running 100 meters on the first lunar day, it stopped after its first sunrise. On the right-hand side, I showed the sketch I showed in Ames in 2009 of levitated dust, which I thought produced the anomalous behavior in the dust detector. Very simple, very straightforward. It's the causes that are the trap. Next slide. Now we deal again with the transparency of the publications. Left-hand side, sadly in Adelaide last September, the presentation about Chang'e 3 was withdrawn, although you can still find the abstract on the IAC website. On the right-hand side is my first drawing, one of my first drawings of the transient effect. I couldn't publish that in 1970, reasons we could get on into later. Next slide. These are the ones published in December 2015 in Planetary and Space Science, together with lots of others. The first one shows the increasing voltage or counts from the vertical solar cell in Apollo 12 dust detector you saw on the moon earlier. Sunrise, then curiously in B, it flattens out. It's just pure sunrise, although the solar cell sees, obviously, light from the entire dawn horizon. It's only after one solar disk in that you start to get the bumpiness, what I'm loosely calling storms, and I'll happily consider alternative names. And on the right-hand side, you've got the equivalent for lunar days 2, 3, and 4. And as I say, I refer you to many, many more of those examples in both the main body of the December 15, 2015 Planetary and Space Science, and particularly in the supplementary. Next slide. Now the question is, how relevant are the 14 discoveries to date to planning, future planning? They all confirm the astronaut views for highest realism. I'll show you that in the next slide. Gaia reports equipment was clogged in mechanisms jammed in every Apollo mission, including zippers, wrist and hose locks, faceplates and sunshades. And the most alarming was how quickly and irreversibly this could happen. Right-hand side has got quotes from the debriefing by Gene Cernan. Next slide. Next slide, please.
Brian, we're going to need you to wrap up.
Sorry?
Wrap up so we can move on to the panel discussion.
I didn't catch that, sorry.
Basically, I'm saying you've gone over time. So if you could wrap up quickly, we'll move on to our panel discussion.
Okay, move on quickly. Next slide. Next slide. The presentations by the commercial firms were most valuable and introduce a realistic note of cost effectiveness, which is of course the basic message of the dust detector. Next slide. That one is, I keep on trying to advertise that, Tommy Gold's discovery in 1972. It's been forgotten and it's not used, to my knowledge, in the literature to date. I don't know why. Beautiful slide. Next slide. Okay, we can just make the point that from the start, the arrangements were made for every principal investigator to get all the measurements by the dust detector. And every principal investigator's tape for his experiment contains the dust detector information in Word 33. Next slide. This is a wrap-up of the astronauts' views of the importance of dust, my interpretation of geologists' views, which is that it's a bit of a nuisance, and the administration views harkening back to 1964. Thank you.
Thank you, Brian.
Next slide. Okay.
Okay, so
That's all, Clyde. There is this video from Washington Post that you know about, and whether you play it or not here or some other time, I leave it to you.
okay, thank you.
Thank you, that's all.
So we have a few
Delighted
minutes
to
left
take
for panel discussion for this session, if the speakers want to come up to the front. And if anybody has any questions, you can approach a microphone. Go ahead, Jack.
I just should say that my commander may have been subject to some hyperbole on the dust. There's no question there was dust in the cabin. There was dust was an issue. I had a slight allergic reaction to it. Another physician who took the suits out of the spacecraft had a fairly extreme allergic reaction. It's one of those things that dust can do. But it is also something that, at least for Apollo, was not an issue. It didn't increase leak rates in the suit. It was there. It caused problems, but the coarser dust was primarily what caused problems in equipment mating and that kind of thing. So, at least for Apollo, it was not a significant issue. Now, longer term, you don't want dust in the habitat. And there are engineering solutions, what I called many decades ago a layered defense against having dust in the habitat that can be implemented, I think, fairly simply, and particularly if we start to really look at what suit designs ought to be in the future. Passive rejection, maybe active rejection of dust off of suits. But it's not an issue that we really should think is going to inhibit any kind of exploration activity so long as you're just a little bit smart about it. And not only that, the presence of nanophase iron in the dust gives you a filter capability through electromagnetic filters that any dust that might happen to get into the habitat, you can filter out. So let's don't worry about it. It's one thing to do scientific experiments to understand it, but don't let it inhibit your exploration.
Thank you. Go ahead.
I wanted to just pick up on a question I think we heard at the beginning of your talk, and it relates to a point that Jack was making, this question about why we're not seeing dust settling elsewhere. Is there anything in the modeling or any empirical evidence that you're seeing that speaks to lateral transport or potential for lateral transport of dust?
So we're working on modeling as well, but it's ongoing. Yeah.
When you have a magnetic field and the nanophase iron in the dust, and any mobility of the dust might be part of what we see at lunar swirls, and we'll be talking about swirls tomorrow. Question I have for you on your experiment where you did the UV radiation, and you had the two movies. I wasn't watching the time of those two. Were those on the same time scale, or was one going faster than the other?
This is time lapse. The experiment was over like a couple hours.
Both of them?
Both of them.
Okay, so one didn't move faster than the other. They were both on that order of magnitude?
It's about the same, is that right? But anyway, the moving is surprisingly fast, and it's pretty scarily fast. And so the current work we're working on is to simulate the condition at 1 AU, and from the income flux of photons or electrons, and to estimate the real rate of dust moving. And what we found is much more complicated than we thought. There are many things can affect the dust movement, like the surface compactness, dust size distribution, and very importantly, it's not a constantly going process. It starts very fast and slows down quickly. And what we think is so the porosity varies with the depth of the regular surface. So when you go deeper, the porosity is less porous. So we like the higher porosity. So you have this microcavity charging effect. It's bigger. So looks like very top layers, they get lofted fast and then slows down. So it's a very complicated process.
Junichi?
Comment. At the bottom of the skylight hole, almost every time in the daytime, we had such a boundary between the illumination area and the shadow area. So we are a little bit concerned about the dust transportation of the area. So Dr. Miyake studied that transportation at the bottom of the hole, skylight hole. So please check and please check the model. And interesting and important issue. Just a comment.
Thanks.
Go ahead.
Excuse my lunar science ignorance, it's out of innocence, but I was wondering about the dust and solar aureole, whether there's been any studies looking at the refractive index of the dust or the solar, like aureole type air distribution of the size particles using solar.
I'm not expert on that, but I don't know.
I don't know. If somebody is an expert, maybe they can find you at the poster session.
Okay, thanks.
All right, last question.
During the constellation phase program, they had the Altair lunar lander, and at the top of the lander there was the module, and then they had solar panels that would be operational during the activity. That was about 10 meters in height by the time you got to that level. Do you see any indication that the Lofted dust would go up to that height and it would settle on the panels?
From our lab experiment, so the maximum speed we got is like 1 meter per second. So it's very low. To get that high, I think it should be higher velocity. It's not that easy. So, but this is the bigger size particles, like a few tens of microns. But the smaller size particles, they can go higher. Yeah.
Thank you.
All right, and that'll wrap up this session. And I think, Greg, are you going to moderate the next panel? Oh, Clive.
Yeah, thanks, Ben.